I'd like to continue with exercise 5.3, and if we go down to the syllabus page, just to kind of refresh where our path to get here, we've actually have 3 exercises that we're doing for ergonomics and work design. First one was concerned with carrying luggage that involves sustained static grip exertions and how long we could maintain those exertions before we experienced objectionable discomfort and the time for exhaustion. In that exercise, we determined the workload on the basis of the weight of the luggage that was being carried versus the strength of the worker. And we looked at some of the effects of hand posture and strength and decided that the best grip or the best hand strength posture was the grip strength to the position of maximum strength for comparison with the weight of the suitcase. In the next exercise, we looked at holding a tablet. Now in this case, the hand wasn't really the limiting factor as much as the shoulder. So to determine the loads in the shoulder, we actually had to calculate how much moment was produced as a result of the weight of the arm and the weight of the tablet. And then we compared that with shoulder strength. In the third exercise, we're looking at clip insertion, and this is different in that it's similar to the first one and it involves the exertion of the hand, but it's different in that it involves a different posture, and it's also different in that it involves intermittent exertions. Additionally, in this exercise, we're asking you to dig a little deeper and look at the workstation layout and how that affects the work method and consequently how much work a worker has to do and what the biomechanical loads and fatigue would be, and use that information to determine a standard time, and finally to investigate some alternative ways of doing the job that would reduce the fatigue and the need for an excessive fatigue allowance. So with that, we can go to the assignment section and of the site, and you'll find the link down here at the bottom that actually takes you to the exercise, and we'll look at that in a minute. But important thing here is that I've put all the resources up here at the top, so they're kind of clustered in one spot, and that's the wrong link, sorry. That's exercise 1.3. Scroll down here to ergonomics and design. Okay, and here's a picture or a video clip of the job being performed. You can either look at this on YouTube or here, but basically the job looks something like this. You can see the worker getting the cards with one hand, the clips with the other hand, opening the clips, putting them on the cards. And I'll just pause this right here because what you're going to see is the most forceful part of this operation is opening the clips. And we've already talked about how we measure the force for that, and we'll come back to how we use those data in a few minutes in our fatigue calculations. So I'm just going to kind of see if I can step through this step by step. So the clip ends up, you see, going on alternating ends of the cards, and the card goes into the bundle, and then the worker gets another clip and gets another card, and the process repeats itself. Okay, so far we've constructed a CAD model of the workstation. Now let's look at how we'll use that to conduct our MODAPTS analysis so we can determine how much time is required for each of these steps. And then we'll follow that with doing a biomechanical analysis. So let's go to the AutoCAD and just take a look at the model we've constructed. So here you see the model. We have a bench that's actually located 7.5 centimeters below the elbow height for someone with 5 percentile female stature and average proportions. We've generated reach envelopes around the elbow in this case because we want it as much as possible, and I emphasize as much as possible because it's not always completely possible to do things the way we'd like it, but we'd like to keep the elbows as close to the body as possible. So you can see here, and actually I'm going to go to a layout view because you'll see things a little bit brighter with a white background, and I'm going to hide the worker, and let's see, my bins aren't showing here, so I'll show the bins. So here you can kind of see what this looks like, and this is kind of what you should have ended up with when you completed your CAD design. Again, here are the bins with the cards. They're kind of staggered here, so you can just to facilitate grasping each of the individual bundles. Over here's the clips. Now I've got the clips kind of neatly arranged here. In practice, you're going to find they're probably jumbled together unless you take special steps to make sure that they are arranged in the best possible way for the worker to grasp them. And then over here are the cards with the alternating clips. So we can now use this information to actually determine the steps required to perform this job. And I've actually made a step in this direction, and hopefully this shows up. Here are the red lines kind of showing the movement patterns for the right and left hand. And you'll see them show up here as I put my cursor over the line. So here's the movement to get the clip and move it into position onto the card. At this point, the worker is going to be opening it, so we've got another clip where the worker is actually maintaining a high force level to hold the clip open as they move it into position. So we can take this a step further, and we can get an idea of how we would classify this using MODAPTS. And maybe it'll even be easier now if I hide the bins, and I'm going to hide the bench. This is really kind of a neat thing about making a CAD model and using the layers, because we can actually isolate the things that we really want to look at. Okay, so here's this line that goes from the a clip handle with the clip in the bin to the position of the clip as we put it on the card. Now here's another neat thing is that we can go over to our property window, and that tells me that the length of that line is 16.6 centimeters long. Well, as you recall from your MODAPTS analysis, in fact, let's go back and just take a quick look at that MODAPTS card that you were given earlier in the term. Come back to the Canvas site, because that's one of the things here on your list. Should be on here somewhere. Carrying case, blah, 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 blah. Somewhere here. MODAPTS reference card. Okay. So you should have a card like this. So if we've got a 16.6, let me blow this up a little bit bigger so you can see it. Zoom in. Well, that helps a little bit maybe. I don't know, I can, actual size, I can zoom in better here. There we go. Okay, so you can see if we got a 16 centimeter move, that's going to be a little more than an M3, but quite a bit less than M4. Now, normally what you do is when you exceed a value here, you go up to the next biggest bin. So I would argue for an M4 here for the move, and then it's going to move it to position just next to the card. So that's going to be a general location, so that would be a P0. But now if we go back and look at our card, our CAD model, okay, here, you can see now we have another move, M1, and that's going to be a P5 because we got to put it precisely in the corner of that card. And also, because we have to apply force to open the clip, we're going to apply extra force for that. So again, if we go back to our MODAPTS card, again, we'll have a P5. And if we scroll down a little bit here, oops, see if I can move this over a little bit, we have an element for extra force, and we would add an X4 to that. Now back to our AutoCAD example. The next step will then be, after the clip is in place, to put the card with the clip back over here. And I can look at this card. Now make sure that you deselect the one line before going to the next line, because it won't give you the total length of both lines unless you use a special command. I'll show you that in just a second. But if we look at this next one, we can see the length is 21.49. Okay, so now clearly if you go back and look at your MODAPTS table, you'll see that that puts you into the M4 bin, so that would be classified as an M4. This is a little easier to position, so we'll call that a P2. to position the cards. And then the process repeats itself by going to get another clip with the right hand, and that will be a 17.5. Again, we're in excess of the M3, so we'll make that an M4 to get the clip, and then that's followed by a grasping this. It's not a simple grasp like a G0, and the clips can be kind of jumbled together, so I give this at least a G3. And if they're really jumbled, if you watch the video, you'll see there's a little bit of fiddling with the clips to get a grip on them. You might even add an extra motion for this one to gain control. So you can see the steps, though, how we can use our CAD model to define each of these steps. Now, and also while we're doing this, I just want to compare this with the opposite hand, so I'll hit escape. Okay, and I'm going to come over here, and you'll see that we have a move to get the card. And if I look at one of these lines to get the card, just make sure I select this. I want the line, not the card. Okay, that tells me it's 11.45, so that actually ends up being less than the 15 centimeter limit of a M3, so that becomes an M3, and we'll call it a G1 because they're pretty easy to get a hold of. And then there's going to be another move about the same distance to move the card into the position and put the clip on it. Since it's moving it to the other hand, if we go back and look at our criteria for terminal element for position, since it's moving it to the other hand, it gets classified as a P0. So right away you can see two things. One, the right hand is really going to be limiting in terms of the number of motions and the time required to complete them. And also the right hand has a fairly significant force burden, which we'll talk about shortly, to open the clips. The left hand only has two relatively short motions and simple terminal elements, so it really is not going to be a limiting factor either in terms of time or in terms of fatigue. Now, one more thing I'll just show you while I got this clip open. We can use a command called list. If I type list, it says select objects. So I'm going to actually, before I do that, hit escape and get out of that. Let me hide everything except my lines. And again, this is a neat feature of the CAD. And you'll see I've also put little X's by where my targets are so they show up. But so now I'm going to type list. And it says select objects. So I'll just take the objects here for the right hand. And I will select each of the lines. Oops, I don't want that terminal. Try this again. I'm going to zoom in a little bit bigger so I can see my lines better. So I'm going to go list, and I'll select the objects being the line showing the movements. Okay, I've got 3 lines. Four lines. Okay, now I'll type return, and now look at right away down here I get a pop-up in my menu that says lines. It tells me what the X and Y, Z coordinates of both ends of the lines are. It gives me the length of the line in the XY plane and the YZ plane and XY, YZ, YX, or Y. XZ, YZ, XY. Okay, so all 3 planes. But it also then gives me the total length in the 3D length. So it says down here 3D length down here at the bottom. So I get the length of this one. Now if I type return, it does the same thing for the next line. You can see the total length for this line was 2.57. I go to the next one, it gives me the length for the next one. It tells me the total length for that 3D length for that one is 21.49. And I go to the last one and it's 17.5. So this is a way I can really kind of inventory my lines, and I can have a kind of a little database of the movement distances, and that of course determines the body part that would be required, and allows me to determine the proper MODAPTS code. So next we'll go ahead and construct our MODAPTS table.